Today, we want to continue looking at Chapter 2, Section 3, where we find the derivative of a function. We're looking at various algebraic styles of function finding, of derivative finding. Today, we're going to look at polynomial and rational functions. And then after a couple of those examples, we'll talk about what the graph of a function can tell us about the graph of the derivative of the function. And then tomorrow we can go on to some different styles of algebraic functions like radical functions and trigonometric functions and exponential functions. But let's start with this polynomial function. We did this a little bit yesterday. We're given a polynomial function and we want to find the derivative of the function. So here we have f of x equals x squared minus 3x minus 4. And we want to find the derivative of the function f prime of x at any point. To do this, we're going to use the definition of the derivative. The definition of the derivative requires an f of x plus h. So when we have f of x is x squared minus 3x minus 4, f of x plus h is going to be x plus h squared minus 3 times x plus h minus 4. That's one of the things that we're going to need in our derivative calculation. So let's plug this function into our definition of derivative, where f prime of x will be the limit as h goes to 0 of f of x plus h minus f of x over h. F of x plus h minus f of x is how much the function changes. That's the delta y. H is how much x changes. That's the delta x. Let's just plug in the function that we have. So we've got the limit as h goes to 0. F of x plus h is x plus h squared minus 3 times x plus h minus 4 minus f of x. And f of x is x squared minus 3x minus 4. So f of x needs to be in parentheses because f of x has multiple terms. And I want to make sure I'm subtracting all of the terms. That requires parentheses. Remember what we want to have happen. We want to plug h equals 0 into our expression to evaluate the limit. But to do that, we have to cancel the h from the denominator. So our goal, we want to just plug h equals 0 into this expression. We want to find this limit by plugging in h equals 0. But that means we need to cancel the h from the denominator. To do that, we're going to need to cancel the h from the denominator. So we plug f of x plus h and f of x into our limits, and then we start simplifying. The nice thing about polynomial and rational functions is that we just need to start simplifying everything to get the h to cancel. I still have to continue to write the limit as h goes to 0 because we have not done the limit as h goes to 0. I'm just going to multiply all this stuff out up here on top. That's going to give me an x squared plus 2xh plus h squared minus 3x minus h, oops, minus 3h, excuse me, minus 4. And then I'm going to subtract these three terms in f of x. So minus x squared plus 3x plus 4. The reason that the polynomial and rational functions are going to be simple is that everything that does not have an h in it cancels out. So notice that we can cancel out x squared minus x squared. We have a minus 3x, cancels with a plus 3x, and then a minus 4 cancels with a plus 4. Everything that doesn't have an h cancels out. And so what we're left with is the limit as h goes to 0 of 2xh plus h squared and that's it. Plus, oh, minus 3h. Missed that one. Now that we've subtracted all the terms that had an h in them, we can factor an h out of the numerator and cancel the h from the denominator. So in the numerator, if we factor an h out, what's left over is 2x plus h minus 3. And then when we cancel the h, we're taking the limits as h goes to 0 of 2x plus h minus 3. Now that we've canceled out the h from the denominator, we can plug in h equals 0 to evaluate the limits. So now that we've canceled the h from the denominator, we plug in h equals 0 to evaluate the limit. And so when h is 0, we're just left with 2x minus 3. Which is exactly what we expected at the beginning if you've seen derivatives before. We start off with polynomial and rational functions because all we have to do is simplify the expression to cancel the h. Let's look at an example of a rational function with a variable in the denominator. And see that we just have to simplify to cancel the h. Any questions on the first example here? So let's look at this rational function.
I've got a question.
Oh yeah, go ahead.
Couldn't you just plug that big equation into Desmos and then just see that it's 2x minus 3? Would that work?
Yeah, we could turn all of our operations over to computers, but that's not what we're trying to do right now.
Okay.
So it's not about getting to the 2x minus 3. It's about what we have to do to get there. Does that make sense?
Okay, so those two are equivalent then.
Yeah, we're just finding the derivative. And eventually we're going to learn the rule where you just go 2x minus 3. You multiply by the exponent and subtract 1 from the exponent. And that's even easier than going into Desmos and asking Desmos. So one of the things that we lose when we do in math classes a lot of times is the fact that coming up with the answer is almost never the point of the problem. So yeah, but that's not what we're on about right now. Although as far as preparation for a future job, unless your job is mathematician, if your job is engineer, when it comes to getting the math done, you're going to be hiring somebody. So whenever professors are like, oh, I'm worried that in an online class, my engineering students are going to hire someone to do their math classes for them. And all I could think is like, well, that's what they're going to be doing in their job anyway. So why not encourage that? You know what I mean? So when we look at this g of x to find g prime of x, we've got 1 over x squared plus 4. We're going to put this function into our definition of the derivative, and the same things are going to happen. We're going to want to evaluate the limit by plugging in h equals 0. So we're going to want to cancel this h from the denominator. To make that happen, all we're going to have to do is simplify the numerator. Every term without an h is going to get canceled, and then we'll be able to cancel the h from the denominator. So let's take a look at the parts. G of x plus h is going to be 1 over x plus h squared plus 4. Let's put this into our limits. So g prime of x is going to be 1 over x plus h squared plus 4 minus 1 over x squared plus 4, all this over h, and I forgot the limit. So we want the limit as h goes to 0 of f of x plus h minus f of x all over h, or in this case, g of x plus h minus g of x all over h. So our goal, just like before, is to cancel the h out of the denominator so we can just plug in 0 for h. Can't do that now because we'll end up with 0 over 0, and that won't work. All we have to do here is simplify our complex fraction. So I'll get a common denominator to add the two fractions, and then we'll be able to combine the numerators. So I'm going to write this h over here, since I have a complex fraction, as 1 over h out front. And I'm going to multiply by, I'm going to get a common denominator for these two fractions. So this first fraction is missing an x squared plus 4. So the first fraction is going to end up being, well, our two factors are going to be an x plus h squared plus 4 times x squared plus 4. That's our common denominator. The first fraction needs the x squared plus 4. And the second fraction needs the x plus h squared plus 4. So once again, this is a rational expression. All we have to do is simplify the expression in the limit, and that will get us to cancel out the h. Once again, this h down here is a 1 over h in the limit, so I could write it on one line. So this h down here in the denominator is the 1 over h. And all we're doing here in the numerator is getting a common denominator. All right, now all we have to do is multiply out the numerator and see what happens. We still haven't done the limit, so I still got to keep writing the limits as h goes to 0. I still have the 1 over h. I haven't done anything with that. That's what's preventing us from plugging in h equals 0. Over here in the numerator, I'm going to multiply x plus h squared, and then plus 4, and then subtract that from x squared plus 4. So if I multiply x squared plus h, x plus h squared plus 4, I'm going to have the x squared plus 4 minus x squared plus 2xh plus h squared plus 4. Oops, put that too early. That's right, I'll just put more parentheses. And we still have our common denominator of x plus h squared plus 4, and then x squared plus 4. And what is supposed to happen is exactly what happens. Everything in the numerator that doesn't have an h in it gets canceled out. I have this x squared minus x squared, minus x squared. I've got a plus 4 and a minus 4. So we've got the limit as h goes to 0. Still have the 1 over h that hasn't gone anywhere, but my numerator is now just 2xh plus h squared. And my denominator is x plus h squared plus 4 times x squared plus 4. Now that we've simplified the expression, we can factor an h out of the numerator. That cancels it out. Then we can just plug in h equals 0. So the numerator here, if I factor an h out, we're left with 2x plus h. So we have the limits as h goes to 0. Now the h cancels out with the 1 over h. And so we have limit as h goes to 0 of in the denominator, and x plus h squared plus 4, and then x squared plus 4 in the numerator, 2xh plus 2x plus h. Now we can plug in h equals 0 to evaluate the limit. Oh, it is, isn't it? I dropped a negative. Thank you. Now I can still plug in h equals 0 to evaluate the limit. Thank you for that. And in the denominator, I've got 2 copies of x squared plus 4 now that I've plugged in h equals 0 to evaluate the limit. So I can simplify that as x squared plus 4 squared underneath a negative 2x. So what we really want is a shortcut to these processes. We don't want to have to do all this algebra all the time. So that's what we're going to learn some shortcuts for. Now, keep in mind, in your future job as a fill in the blank, I'm not sure what it is. I'm not allowed to look into the future and see what your future jobs are. The administration told me you can't do that. It's invasive. And I'm like, I don't tell people what I see in the future. I just like try to use that to shape the lessons. And they're like, oh, no, you can't even look. So I just tell that I'm not looking anymore. I'm just kidding. I'm totally not looking into the future. So we're going to learn shortcuts to using the definition of the derivative, and they will be welcome shortcuts until they get more complicated, like we have to start using the chain rule. But it's still going to be better than the definition of the derivative. And we're going to spend some time getting good at using all the different rules, product rule, quotient rule, chain rule, and such. And then we're going to notice or be reminded of, or maybe we won't know this for years, that if you're about to find in your job, if you're in your job as a future fill in the blank, whatever it happens to be, if you're about to use the chain rule to find the derivative of a function by hand, you're probably about to get fired as well. So it's not that we do these things by hand. I'm not here to train you for your job as a future fill in the blank. You hired me to teach you math, not train you for your job. Does that make sense? So there's a lot of times we get bogged down into details, especially when the details look like this, even when they're just as simple as this, and we don't want to do all that writing. And so we're like, oh, when am I ever going to do this? At least I got to tell you, probably never, but that isn't the point. You know what I mean? So we will eventually learn shortcuts to using the definition of the derivative, and it will be good. We will eventually like next week, learn shortcuts to using the definition of the derivative. But for the most part, when these kind of calculations actually come up in application, the functions are way more complicated, and we're just going to have a machine run approximations for us. And we're just going to model things that way. All right, so eventually problems will look like f of x is equal to x squared minus 3x minus 4. And you will just immediately write down f prime of x is 2x minus 3. And then for those of you who are interested in what the pattern is, I'll put another one up there. Let's suppose that p of x is 5x to the third minus 4x squared plus 7x minus 8. Then p of x is 15x squared minus 8x to the first plus 7. That should give you an idea about how you can find derivatives without using the definition, because this would be not difficult, but tedious, because I'd have to take an x plus h to the third, an x plus h squared, and x plus h times 7, combine all the like terms just to cancel the 8, or the h. G of x, which looked like x squared plus 4 to the negative 2, we want to learn rules so that we can just write g prime of x as negative 2 times x squared plus 4 times 2x. Did I drop a 2 somewhere? Oh, it wasn't to the negative 2. My mistake. I started off with the wrong function. Eventually, we'll look at g of x as x squared plus 4 to the negative 1, so that we could just write g prime of x as negative 1 times x squared plus 4 to the negative 2, and then multiply by 2x. That's where we want to go with this. We want to learn the shortcuts so we can avoid the definition of the derivative. But once again, the skill is not about actually finding the derivative. I like to think of it sometimes when we're doing exercises like this. I like to think about it like going to the gym. I've heard people go to the gym to exercise, and they lift heavy things up and then they put them back down again. It's not about doing this fast, because the end result is that the weights are back on the floor. So why not just leave them there in the first place if you're just trying to be fast? But we're not trying to get just to the answer where the weights are back on the floor, or even better, back on the rack, because then we would just leave them there. The point is picking up the weight and lifting it up in a weird way. Think especially in terms of lateral raises. No one ever questions their trainer why they have to do lateral raises, because that's just not how you pick things up. But we know that by doing lateral raises, you exercise particular muscle groups that you aren't exercising in other exercises. And so it's overall good exercise. That's what we're doing here in math. Math is like exercise. They have programs like Lumosity that are supposed to be good exercise for your brain. You want more good exercise for your brain, make it math. It's more fun doing Lumosity because it's designed as games, and games are fun. So if you want training doing something that isn't fun, but it is good training, math, because it's not fun, but it is good training for your mind. That make sense? So that was part one. That was our algebraic technique of the day. With polynomial and rational functions, if we're using the definition of the derivative to find the derivative of a polynomial or a rational function, all we got to do is put it into the definition and simplify. Just simplifying will cause the h to cancel, then we can plug in 0. Tomorrow, we're going to look at radical functions and what we're going to have to do to simplify the definition of the derivative for a radical function. What I want to do next is think about what the graph of a function tells us about the graph of the derivative. And we're going to consider the function f of x is x squared minus 3x minus 4, because we already know its derivative, f prime of x, is 2x minus 3. So let's jump over to Desmos and take a look at these functions. Oops, I had the wrong stuff plugged in. So let's jump over to Desmos and take a look at these functions. That's not what we want to look at. Ah, here we go. All right. So here we have the graph of f of x. That's this blue parabola. We can see the zeros. We can see the vertex. And we also have the graph y equals 2x minus 3, which is the derivative of the function. So you see the intersect here. That's not what's important. We see that we have a 0 at 1.5. Remember that the derivative is telling us the slope of the line tangent to the function at a given point. So if you'll notice, down here at the vertex of the parabola, when x is equal to 1.5, that's when the tangent line is horizontal. So if I draw a horizontal, y equals negative 1. F of 1.5. So if I graph y equals negative 6.25, there's the tangent line to the parabola is horizontal. So the slope of the tangent line is equal to 0. Now, if I look at the value of the tangent line at 1.5, the tangent line at 1.5 is equal to 0. So if I look down here if I look at this point, when x is equal to 0, I got the point 0, negative 4. If I want the slope of the tangent line when x is equal to 0, I can plug that into my derivative. So if I look at f prime of 0, we get negative 3, and that's the value of the line when x is equal to 0. So the slope of the tangent line when x is equal to f of x when x is equal to 0 is negative 3. If I graph that line with a slope of negative 3 and a y-intercept of negative 4, oops, negative 3x, then I can see that we get the tangent line. We zoom in, we can see that the orange line gets really close to the blue parabola. They touch at 0, negative 4, and then the orange line continues doing its orange line thing. So the value of the derivative tells us the slope of the line tangent to the original function. Notice that the parabola before 1.5 is decreasing. So all the slopes of the tangent lines before 1.5 are going to be negative. and then take a look at the derivative, the values of the derivative are negative all the way up to 1.5. After 1.5, the parabola is an increasing function. The values are going up. And so we're going to see a positive slope. And the values of the tangent line after 1.5 are positive. So the derivative of a function will tell us about the direction of the function. If the derivative is negative, then the function is decreasing. If the derivative is positive, then the function is increasing. And so we can read that the other way. When the function is decreasing, the derivative will be negative. And when the function is increasing, the derivative will be positive. When the function is flat, that means that the derivative is going to be equal to 0. Or the other way around, when the derivative is equal to 0, then the function is going to be flat. We'll have a horizontal tangent line. So that's an important connection that we want to make between the graph of the function and the graph of its derivative. So if the function is increasing, that means the derivative is positive. If the function is decreasing, that means that the function, or the derivative, is negative. If the function is flat, then the derivative is equal to 0. This is extended. This is just more of the idea. This is just more of the idea that the derivative tells us the slope of the line tangent to the function. Any questions? So let's suppose that we're looking at the graph of a function and we want to sketch the graph of the derivative. So I'm going to draw a function that we'll just call p of x, and we're going to want to use that information to sketch the graph of p prime of x. So let's see. So p of x is just going to look like, it's going to go up, down, and up again. What we want to read about the graph of P of X is where it is increasing and decreasing. And then we'll use that information to determine where P prime of X is positive and negative. So the first thing that we need to consider is where is the graph of P of X increasing, decreasing, and flat. So there are 2 points that are of interest when the P of X flattens out. So I'm going to give those names. I'm going to say this happens at x1. And there's another point where the graph flattens out, and I will call that x2. Math variables don't get interesting names. It's probably why I don't have kids, because I would just give them names like math variables. First kid would be like x1. Next kid would be x2. Then we have x4. People would wonder what happened to x3. I'm like, well, we don't talk about x3. But then that would make me less just a mathematician with no clever ideas for names for the kids, and just kind of like make me more like Elon Musk, who decided to be cruel to his child. So we're looking for where P of X is going to be increasing, decreasing, and flat. So we notice that for x less than x1, before x1, P of X is increasing. P of X is increasing. Therefore, P prime of X is positive. So for x less than x1, before x1, P of X is increasing, so P prime must be positive. So it must be above the x-axis. When x equals x1, P of X is flat. Therefore, P prime at x1 is equal to 0. Now we've got some important information to put together. We can draw the graph, and I'm going to draw it directly underneath this graph. I'm going to make another x-axis down here. So x1 we know that P of X is flat at x1, so P prime of x1 is equal to 0. I can actually mark a point on P prime of X. Before x1, I'm going to have to draw P prime of X positive, so it looks like P prime is going to have to decrease down to x1. Let's go on to the next part. Between x1 and x2, P of X is decreasing. Therefore, for x between x1 and x2, P prime of X is negative. So I'm going to draw P prime below the x-axis between x1 and x2. Then we're going to note that when x is equal to x2, P of X is flat. We have a horizontal tangent at x2. Therefore, P prime at x2 is equal to 0. So here's another place where I can mark a 0 on my graph of P prime of X. Before x1, I'm going to draw P prime of X above the x-axis. It'll hit 0 at x1, and then between x1 and x2, I'll draw p prime of x below the x-axis. And then for x after x2, p of x is increasing. Therefore, p prime of x is back to being positive. So now we've used our information, the information that we see in the graph of p of x to sketch what the graph of p prime of x looks like. I'm going to draw something that's positive before x1, hit 0 at x1, be negative between x1 and x2, and then be positive after x2. So it looks like I'm going to have to draw something down negative that's going to have to turn around so I can get back up to x2, and then after x2 be positive. Then before x1, I have to draw positive, but I have to land at 0 at x1, so I'm going to have to draw p prime decreasing before x1. So there's a sketch of the graph of p prime of x. Now, this is a process that we're learning about in math, so we have to know it backwards and forwards. So tomorrow, we're going to look at the graph of p prime of x and decide what that tells us about the graph of p of x. I'll probably use a different function name. Any questions on the graph business?
Yes, for fresh knowledge, is the flat is same at the vertex or no?
We don't want to. A parabola is flat at its vertex, but we don't always want to call flat points a vertex. Vertex is a little bit more specific. So I wouldn't want to just use the word vertex all the time. So, and points where the graph is flat do not always look like high points or low points. So for example, if we have a graph that goes up and then flattens out and then continues to go up, a vertex kind of means things are turning around. But here's a point where the graph is flat, but it's not a vertex.
Oh, okay.
Good question. So the graph is flat, but the graph doesn't take this opportunity to turn around. It just flattens out, takes a breather, and then heads on back up, continuing increasing. Any other questions? All right. So tomorrow we're going to look at this problem in reverse. I'm going to give you the derivative. We're going to look at the graph of the derivative, and then we'll use that to draw the function. We'll also learn how to deal algebraically with radical functions and the definition of the derivative. I also want you to make sure you look at how I found the derivative of the polynomial functions and see if you could figure out a shortcut. Figure out what the shortcut will be, because that will be a good way to discover what's going on. Take a guess at how that's supposed to work, and then see if it applies in other scenarios. Any questions, comments, snide remarks? All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.